give an overview of our results of the MIXSEL project. This was funded for the phase 1, and we'll have a continuation of the MIXSEL project also in the phase 2. In a different constellation, because we want to consolidate our results and our activities. So this is an activity and a collaboration between ETH Zurich from my group, then Professor Elie Capon from EPFL, then Thomas Südmeier, who became a new professor at the University of Neuchâtel, and Professor Bernd Witzigmann, who was originally an assistant professor at ETH Zurich and then moved to the University of Kassel for a permanent position. So the goal is to make compact ultrafast lasers. So ultrafast lasers is standing for short pulsed lasers, lasers that produce a train of pulses in the pico and femtosecond regime. It's kind of like a clock that comes at the same time producing these pulses. So this is an ideal source for any kind of clocking or communication. Of course, as you know, if you have a bit on every time, then of course you don't have any information, and so this is normally then combined with an external modulator to do the information onto it. And at this point, when you look at for the long haul communication, this is normally still done with CW lasers, additional modulators to carve the pulses, additional modulators to then get the information onto the pulse train. And it's clear on the long run, everything gets faster. I mean, it only slows down maybe a little bit, but we will increase our bit rate as we move on in life. And from a certain point on, it simply does not make sense to use a CW laser and carve the pulses. So these short pulsed mode-locked lasers are actually very happy lasers who keep producing these pulses in a very stable mode of operation, and the cost of these lasers has been very often the limiting in the application. It is also clear that in the computer world that a good stable clock will be needed for the multi-core processors. Right now the computers work with a lot of cores, but these cores are not working in parallel computing, and if we want to do that, we need a clock so that all these cores are doing the computation steps synchronized with not too much effort. Another big application range is that these short pulses take the energy and collect it in a very short time frame. So you get a lot of peak intensity here. And you, in addition, because it's a laser, you can also focus it down. And this can be used for imaging and for nonlinear imaging, where you really need the high peak intensity. So one of the big market is, for example, the multiphoton biomedical imaging, which also has been hurting by the cost of the ultrafast lasers. So again, here we did during this project, we developed prototypes of the lasers that we developed, and first images have been generated with this multiphoton biomedical imaging. Of course, you can also use it to a certain extent for some material processing with the power that you can get with these more compact lasers. Then the last application range is that these lasers, because in the time domain, they have these really short pulses, and in the frequency domain, Fourier transform, it means that you have a broad spectrum, and because you have a pulse train, this spectrum is not continuous, it has actually a comb, and this comb has huge applications for metrology out there, and that's why in the second phase we also get ABB and other companies involved using this kind of lasers, because again, all these applications have been proven to be really important, but the cost of the laser has been always the limiting situation for all these applications. So with this motivation, I hopefully can explain to you why we're doing what we are doing. So traditionally, when you come from the solid-state laser the dye-pumped solid-state laser. You have a gain element, which is a solid-state laser, and a modulator, which is producing the short pulses. So these kind of lasers require packaging because you need this modulator, and you need the gain, and you need to make a nice cavity, and that makes it a little bit more expensive. A big breakthrough came 20 years ago by actually reducing active modulators with a passive modulator, which we refer to as the so-called semiconductor saturable absorber mirror, which looks from far away just like a mirror, but by putting it in, it's a nonlinear mirror. Instead of getting CW light, continuous light, you get pulses. So it's a very successful a device that is now implemented in industrial application. All ultrafast lasers industrial are based on this pulse generation process of these dye-pumped solid-state lasers. Now, when we move away from the solid-state laser and actually go to the semiconductor laser, then we have the advantage that we can integrate the saturable absorber, this nonlinear mirror, into the laser, because then the laser is semiconductor, the modulator is semiconductor, and we can make it a single wafer structure which has an optical thickness of about 10 micrometer, and the whole packaging will be much cheaper. And this laser has the complexity in principle less than a VCSEL. Has the possibility for electrical pumping, for optical pumping, and there are, of course, normally when you come from the semiconductor laser business, you say, what a dumb idea to use optically pumped semiconductor laser. Okay, because the semiconductor have, of course, the advantage that they can be electrically pumped. So why on earth would you consider optical pumping? Optical pumping, as I try to convince you during this talk, has very much an advantage because you can scale the power. And the complexity to optical pumping is not so good for here. For example, Coherent has a big product package on optically pumped semiconductors, which is very successful. Okay? Now, this looks trivial, right? You just take the semiconductor absorber and integrate it into this MIXSEL structure. So the MIXSEL is basically this is the so-called, so that's also interesting, there's a language here. So the laser that is in your computer mouse, right, this is a VCSEL, which is without the E, so it's a vertical cavity surface emitting laser. Now, because we use actually an external cavity, we call it then the VEXEL, the vertical external cavity surface emitting laser. And the MIXSEL with the integration of the saturable absorber is a device concept that was invented at ETH here in Switzerland. And when you invent something, you create a name, right? And we called it the MIXSEL to pick up on this surface emitting laser acronym part, to add it to this family of lasers, and it stands for modelocked integrated external cavity surface emitting laser. Now you would think this is a trivial concept, right? You just take the absorber and integrate it, but there are a little bit of physics that you need to understand to make this happen. Because the process, how you produce these pulses, means that you need to have this loss modulation needs to, when you have a pulse going through this device, needs to saturate faster than the gain, so that you have a net gain window here that is supporting your short pulse. And if this is the same semiconductor like in the gain, they have the same saturation properties, and that wouldn't work. Now you can do it traditionally. Initially we did it by just focusing stronger onto the cesium, so it saturates faster. But when you integrate it, then the mode size is the same inside the absorber as in the gain. So you cannot use that. But of course it's a multi-layer structure. You can do field enhancement for the experts. But then it's a resonant structure. It's very sensitive to the growth parameters, and it is a nightmare for production. So we put in a fair amount of effort in the material development, actually moving to quantum dot materials, and we developed a cesium structure, which is nice. We can develop this in 2 steps, right? We still stay in this hybrid way of operation that we have in VEXEL and the cesium, but we then design the cesium such that the mode size is the same as in the gain, so that we can afterwards do the integration. And that helps us a lot because we can explore a lot of things. We can turn knobs here when it doesn't work. If you right away go from this to an integration structure, you don't have too many knobs. It either works or it doesn't work, and that is pretty frustrating because you go through a lot of processing with your graduate students and you want to keep them happy. And so you want to make some sanity checks along the way. And during this project, we successfully actually did that by moving to quantum dots. So QD stands for quantum dot saturable absorber, whereas the quantum wells stands for quantum well saturable absorber. So our initial goal for this proposal was really to demonstrate this MIXSEL concept, both electrically pumped and optically pumped. And you really look at the feasibility studies in terms of what kind of a parameter range can we get from 1 gigahertz to 100 gigahertz. Please remember, 50 gigahertz is given basically just by the round trip time of these pulses inside this laser. And so for 50 gigahertz, your laser length is 3 millimeters. And we wanted to see how good do we get pico, how do we get femto. Our initial goal was get electrically pumped MIXSEL more than 100 milliwatt to make it relevant, or optically pumped MIXSEL clearly more than 500 milliwatt. And we did some first feasibility application in biomedical within our EU FastDot project for optical clocking. We had collaboration with Intel, and the frequency metrology we did actually with Pierre Thoman from University of Neuchâtel, who retired meanwhile, and Thomas Südmeier took over. And you know, certain things turned out to be much better than we expected, and other things turned out to be much harder than we expected, right? This is life. So let me show you some of the highlights. So what turned out to be much better than we expected was the average power that we could get out of a MIXSEL in the picosecond domain. A picosecond is sufficient for clocking application. You actually don't always want to have a lot of bandwidth, otherwise you have to deal with it. And you know, we actually obtained over 6 watt of average power. You remember we wanted more than 500 milliwatt, 0.5 watt. And we did that at 2.5 gigahertz at 960 nanometer based on indium gallium arsenide technology. And the overall performance in terms of pulse duration and average power of this result is still a world record in terms of the performance today. Then we also showed that you can just change the cavity length and make the cavity length shorter to get to the 10 gigahertz and still at 2.4 watt. And that is this result, which is also very nice. I mean, normally the performance of these lasers is excellent in terms of the pulse properties. At 10 gigahertz, you can then resolve the axial modes in the spectrum. And the frequency comb of a modelocked laser you can then resolve on an optical spectrum analyzer. We then also pushed the femtosecond domain. We initially, as I said, do the step in between where we have the same mode size on the gain and the absorber to make sure that we before we do the integration step. And one of our milestones was to demonstrate more than 1 watt. With 780 femtosecond at 5 gigahertz, and this was definitely a result that got a lot of attention worldwide. We actually also started during this period a new conference at Photonics West, the MIXSEL conference, which is actually now a 2-day, full-day conference with a lot of industrial participation. Meanwhile, there are some nice results from commercial people who are now pushing this femtosecond performance even into the multi-watt regime, which actually shows that this technology is good. They still focus onto the cesium, so their result would be not so easily transferable to a MIXSEL device. We now are still in the process of trying to integrate that into the MIXSEL device. We have to compensate for the annealing that is taking place during the growth, and so this is work under progress, but we are confident that we can get this one going as well.